Hello there, this is Glenn Berry with Dr. DMV LLC, and I'm back with another video. In this video, we're going to take a look at some queries that let you measure sequential read throughput using SQL Server, and we're going to look at it from two different perspectives. The first one is looking at storage performance, and then the second perspective will be looking at memory performance. So what I have going here is I have my Ryzen 9 5950X system, and I've got three different M.2 NVMe storage devices connected to it, along with some other storage. So I've got things laid out pretty much the best that I can with my current system. So we're going to measure how well that actually performs. And when you do a lot of synthetic benchmark tests, quite often you'll get skepticism from your storage administrators or your SAN administrators, because they'll say, well, that's not SQL Server, that's not a real workload. And running these queries against any kind of a storage subsystem is very illuminating. You'll find out a lot of information by doing this. The first thing we're going to do here is run the checkpoint command. And that just flushes any dirty pages that SQL Server has in the buffer pool to disk. And then the second thing we're going to do, which you should not ever do in production, is run dbcc drop clean buffers, and that flushes all the data out of the SQL Server buffer pool. So then when we run our next set of queries, it'll force the storage subsystem to service the request instead of pulling it from the buffer pool. And then we're going to turn on set statistics IO on and set statistics time on. Those are just two commands that are useful for measuring time and IO statistics. Next, we're going to switch to a database that has a fairly large table that will fit in the SQL Server buffer pool. And my system has 64 gigabytes of RAM, so I want to have something that will fit in that buffer pool but still be a fairly decent size. I have a table here, and we can run this command right here, sp space used, to find out how large this table is, and that's roughly 18 gigabytes. But if we actually run the calculations, we can divide the kilobytes by 1024 to get megabytes. And then it turns out that's how many megabytes. So it's roughly 18 gigabytes. And that's how big this table is. And when we run this query right here, select count star from the table with this index hint right here, that's going to force it to do a table scan or a clustered index scan, whatever the case may be, and read that entire table from storage into the SQL Server buffer pool. So we'll go ahead and do that and see how long it takes. And it came back fairly quickly because I've got extremely fast storage on my workstation. And if I go to the Messages tab, you can see right here that it took 2.9 seconds. So that's how long it took to read in 18 gigabytes of data. And I have a calculation down here that helps you understand how fast that actually is. And if you go back and look at the Messages tab here, you can see how many logical reads we had and how many physical reads we had and how many read-ahead reads we had. You can plug this number into the calculation right down here and multiply it times 8, because it's 8 kilobytes per page, and then divide that by how long it took in milliseconds. And if you run that, which I did before, you're going to get roughly 6.6 gigabytes per second. And that's how fast my storage subsystem can read data into the SQL Server buffer pool. And when we ran the command up here, dbcc drop clean buffers, that cleared out the buffer pool. So when we ran that query that we just ran, it read it from storage instead of from the buffer pool. Now, before we go any further here, let's take a quick look at the database that we're using for these tests. This query right here will let you see how large all the files are and where they're laid out on my storage subsystem. So this database is called No Compression Test, and I've got a main file group, and then the primary file group, and then the transaction log file. And we can see that I've got one data file, the primary data file is on the S drive, and then I've got another data file in the main file group on the S drive, then I have one on the R drive, and one on the C drive, and then another one on the C drive, and there's a reason that I have it laid out that way. But I've played around with it a little bit, and this is sort of the best that I've been able to do so far with the equipment that I have available. Now, if we go back to the queries, another query that I want to run that's going to take a few seconds is going to look at how much data is in the SQL Server buffer pool and what tables and indexes that it's coming from. And so when I run this will take a few seconds to come back. Even on my very fast system, it's going to tell us how much space and memory is being used up when we ran that previous query to read everything in from that one table into the SQL Server buffer pool. So that took 29 seconds to come back, even on my fast system. But the point of that was that in the main file group, this index, the clustered index for this table, is using this much space in the buffer pool. And it has this many rows in the table, and it's not using SQL Server data compression. And that's on purpose because I wanted to have 18 gigabytes of data to read into the buffer pool. Now let's take a quick look at my equipment that I've got to work with here. So running Crystal Disk Info, we can identify each one of the disks in my system. And then I ran Crystal Disk Mark on the drives that have any SQL Server database files for this database. So starting off, we've got the C drive right here, and this is the Crystal Disk Mark for the C drive. It's a Samsung 980 Pro. It's 500 gigabytes, and I'm not sure what's going on with this write result there. That's unusually low. It shouldn't be that bad. This is a PCIe 4.0 NVMe M.2 drive, and it does very well for read sequential performance, as you can see right here. Then we've got some data files on the S drive. So this is a 1 terabyte 980 Pro. So it's just a larger version of this guy. And this is what you should normally see for write performance, but that's not relevant here. We care about the read performance. So we've got a lot of read performance between these two drives. And then we've got a data file on the R drive, which is a 970 Evo Plus. It's 1 terabyte, and that's only PCIe 3.0. So you can see the read performance is quite a bit lower. That's about the limit of a 4-lane PCIe 3.0 interface. And then we have the transaction log file on the L drive. And the L drive is an old-fashioned SATA drive. It's a Samsung 860 Evo, 1 terabyte. And that's not actually being touched in these tests, but just for completeness, I wanted to show that. And I've got, again, the Ryzen 9 5950X CPU, and then my motherboard is a Gigabyte B550 Aorus Master. And this particular B550 board is sort of unusual because it has 3 M.2 slots that are all connected to the CPU, and they're all PCIe 4.0. And when you use the second and the third slot, it changes the video card PCIe from 16 lanes down to 8 lanes. So you can have more lanes available for storage. And one thing I could probably do to optimize this system more would be to swap out this R drive and put a PCIe 4.0 drive in its place. But probably one thing that I'm starting to run into with this system is just a shortage of PCIe lanes and a shortage of throughput that I can get with a mainstream AMD system because I don't have as many lanes as I would have with a Threadripper system. Okay, so now we've measured our storage performance, and now it's time to measure our memory performance. So what we're going to do here is run the same exact queries we ran before, but we're not going to run DBCC drop clean buffers. We're going to leave the data in the buffer pool, and then we're going to use a hint right here to set max degree of parallelism, max stop, to different values. So we're going to start off with max stop equals 1. And when we run this query, it means only one of our 32 logical cores on the system is going to be used for this query. And that's going to slow it down quite a bit. So when we run this, we can see what's happening here is one of our processor cores is spiking up for a few seconds because it's doing the work to read all that data from the buffer pool into the CPU. And if we go to the Messages tab, we can see that it took about 7.1 seconds. And when I tested it before, it was slightly faster. It's going to vary a little bit every time you run it. And if you punch that number into this little calculations here, it'll give you how many megabytes per second. So we're seeing about 2,784 megabytes per second of sequential read throughput from the buffer pool when you restrict it to max stop equals 1. So if we run the same thing with max stop 2, now we're going to let 2 cores work on it, and we can see 2 cores spiking up for a few seconds, and that came back significantly faster. It came back in slightly over 4 seconds. And when I was testing it, it was about the same. So you can see that the throughput has gone up to 4.7 gigabytes per second roughly. So if we do the same thing with max stop equals 3, you would expect this to go up a little bit more. And that in fact is what happens. And if we go to the messages tab when it finishes up, it's going to tell us that it's 2.9 seconds. So it's slowly getting faster and faster as we add more cores. And you can see what's happening if you look to the right at Task Manager. We'll go ahead and do it with max stop equals 4. And so we can see that it's using more cores and coming back more quickly. And it came back in 2.2 seconds now. And if you ran the calculations, that's getting to be about 9 gigabytes per second reading from memory when you've got it throttled down to only max stop equals 4. So let's go ahead and do max stop 5 and see what happens, see if it gets any faster. And so we would expect it to come back quicker, and it does. It's down to just slightly over 2 seconds. And if we run the same thing for max stop equals 6, it should get a little bit faster, but we're starting to kind of flatten out here. And now I'm kind of curious why that is, and maybe we can figure that out in another video. So if we go to the Messages tab, it's slightly under 2 seconds. And by the way, the max degree of parallelism at the instance level for this instance is set to 8, which is what you would get on my system when you run SQL Server 2019 and accept the default settings from the setup program, which you don't have to do, but that's what it's set to right now. And you could always override that. So we'll go ahead and run it for max stop equals 7. And again, you can see more and more cores bursting to read that in parallel. And if you look at the Messages tab, it's kind of flattened out. It's slightly under 2 seconds. So then we'll go ahead and just do index 0 and not have a hint here and see what happens now. So it's going to use 8 cores, and that came back quite a bit faster, a little bit less than 2 seconds. And then finally, the last one in this little set is we're going to set the query hint to max stop 0. And that means SQL Server can use as many cores as it wants, and it will ignore the instance level max stop setting. And we can run that, and that comes back extremely fast, 806 milliseconds. And when I was running it in test, let's just run it again for the heck of it, see what happens. Came back in 769. We are doing about 27 gigabytes per second when you let all the cores work on it in parallel. This is a way of measuring your memory performance with different max degree of parallelism settings. And I think it's kind of interesting because it shows you what the entire system can do when it's not throttled back. And you can see what's happening when it's using the default instance level setting. And then you could see what's happening if you had the setting either in a query or at the database level set to a really low value. That's really going to have a big effect on your sequential performance from memory. Let's summarize what we've done here. We took a fairly large database with a large table that would fit in the buffer pool of my SQL Server instance. And we purposely flushed the buffer pool so no data was cached in memory. And then we ran a query right here that forced it to read that entire table into the buffer pool. And we forced the storage subsystem to do that work, and we measured how long that took. And the point of doing that was to measure the real world performance using SQL Server of our entire storage subsystem. And how you have your data files laid out and what kind of underlying storage you have and how it's configured has a big effect on that. And if you do this during a maintenance window against your SAN and you get really poor performance, that means there's a problem with your storage subsystem, and there's no way your SAN administrator can deny it. They can't say that, oh, that's a synthetic benchmark and it's not real. It's actually measuring the sequential read performance of SQL Server with the storage subsystem. So that was the first part of what we did. And then the second part of what we did is we ran a bunch of queries using this query hint and setting max stop to different values, starting off with one core and going all the way up to all the cores in the system to measure how fast we could read from memory and how fast the CPU could consume all that data coming in from memory. And the idea for this came from the old fast-track data warehouse concept that Microsoft used to push pretty heavily with the server vendors. And you wanted to have a balanced system that had the storage and then the memory and the CPU capacity so you could read data really quickly for big data warehouse reporting type queries. So that's what the point of all this is. And you can easily run these same tests on your system during a maintenance window with your own data. Just pick a database with a large table that meets that criteria and then try doing this. This is Glenn Berry with Dr. DMV LLC, and I want to thank you for watching this video. If you liked the video, please hit the thumbs up button. If you have any questions, please leave a comment. And finally, if you want to see more content like this, please subscribe because that really helps the channel out.